Have you ever sat on a beach at night and wondered at the stars, the galaxies, the planets? Maybe you've even dreamed of being an astronaut, of sailing through the stars and onto Mars and beyond. I have heard that TED audiences are adventurous. I am looking for adventurous people today to ask you to imagine the adventure of a lifetime, a round trip to Mars. My early days were in Brittany, a coastal area in France, where I used to love sitting on a beach at night and watching the stars. I dreamed of stars, I dreamed of traveling to the planets, but I never ever thought that my life and passion would become one where I was helping to build the starships, the rockets that would reach for truly uncharted frontiers, Mars and beyond. My life and work now involves research on space travel and plasma rockets. And many nations get together to develop the space missions of the future. Of course, our sights are set onto Mars. We are here on planet Earth, which is surrounded by a gaseous atmosphere which contains mostly air, which we breathe in and out. Outside this cocoon is space and deep space, which contains the solar system, our galaxy, the Milky Way, and other galaxies. 99% of ordinary matter in the universe is in the plasma state. Most stars are made of plasma, and we want to use this state to propel our rockets into space. So plasma is the fourth fundamental state of matter, starting from solid to liquid to gas to plasma by raising the temperature. Just imagine an ice cube which would melt in your hand to become water as a liquid. You could then boil this water in a kettle and get water vapor, and you could put more energy and heat into this water vapor to dissociate and ionize the water molecules so that they could reach the high temperatures of the plasma state. So a plasma is a very hot ionized gas which contains light and photons and charged particles, the negative electrons, and the positive ions, and sometimes negative ions. These charged particles give the plasma very interesting conductive properties, similar to those of metals. So the sun is a very, very hot ionized plasma with a temperature of 15 million degrees Celsius in its core, 6,000 degrees at the surface, a little bit cooler, but still very hot. In the center, you have fusion reactions of hydrogen atoms, which releases an enormous amount of energy in the form of radiation and light, and of charged particles. The charged particles form the solar wind, which expands and flows out of the sun's surface and starts traveling into space and impacting on anything it will find on its way. Fortunately for us, Earth is also a big dipole magnet with the North and the South Pole, and this creates a protective magnetic shield around the atmosphere, which is called the magnetosphere, and this shield limits the impact of the solar wind onto Earth. And this interaction can be seen in the polar regions in the North and South Poles, and you can see these beautiful northern and southern lights from Norway or from Canada or from Antarctica. But a naturally occurring plasma familiar to us all is lightning strikes. These are very powerful, with up to 1 billion volts of electricity in the air looking for a path to ground or to Earth. So when lightning strikes, it heats and ionizes the air along its path, and you get a plasma. So how about we make a plasma or mini lightning strike now on stage? I'm going to use this device, which is called a Tesla coil. This was invented by Nikola Tesla over a century ago. He essentially gave us alternating current or electricity as we have it now. So when I turn this on, what happens is it produces very, very fast oscillating signal here, about 10 oscillations per microsecond, so very fast, but it is rather large voltage. This means that when I turn this on, and I bring this closer to a metallic or grounded surface, I can trigger a spark of plasma. You see that light? So the light are the photons which are emitted by the plasma. You don't see the charged particles, but they are here, and they carry the current from the tip through the plasma and to ground. Another device you're very familiar with is the fluorescent tube. So this contains neon gas. So again, if I turn this on, I can radiate energy into it and ionize the neon gas which is in here. So this is a lighting device, a few dollars. You know what this is? This is a flipped packet of chip. You may have noticed that you have a very, very thin coating here, also done with plasma technology. This acts as a barrier against oxygen and water. You don't want your chips to get soggy and to go off, do you? No. Talking about chips, this is the really fabulous chip, or many of them. You know what this is? This is a silicon wafer which is covered by millions and millions of transistors. These transistors are the engine in your computer, in your tablet, in your digital camera, in most electronic devices. They are very small because they are manufactured using plasma technology, and in particular the ions in the plasma. In the 1960s, to manufacture a computer as powerful as your mobile phone would have cost $1 million to manufacture. It would have been the size of this stage. And now, thanks to plasma technology, you can hold it in your hand and it costs much less. Now let me take you to my world and passion, plasma rockets. There was a trigger in my life quite a few years ago when I had the opportunity to spend considerable time with NASA crew of shuttle flight STS-111, which went to the International Space Station for about 10 days. The crew was in its final stage of training in Houston. And it is important to say that to access space, we must use powerful chemical rockets, which burn a huge amount of propellant to give us a force big enough to overcome gravity during takeoff. But when we are in orbit around Earth, we can deploy plasma rockets. And you know what? This is the simplest plasma rocket you can think of. This is the fluorescent tube again. We can radiate energy into it, ionize the gas, make a plasma. If you chop one end off, the plasma will expand into space. A force will be created in the opposite direction. This is the principle of your plasma rocket. It will start traveling into space. When the plasma exits this rocket, it looks like this photo there. Why do we want to use plasma rockets? Because they are very fuel efficient. You can actually go from Earth orbit to the Moon orbit with just 80 kilos of gas, like what you would have in your car tank. And what we're trying to do, we are trying to accelerate the plasma before it exits the rocket to further decrease this fuel consumption and increase the thrust. So the prediction is that you could go for a round trip to Mars in less than a year, as opposed to many years using conventional chemical rockets. But what we need to do is we need to test these rockets here in the laboratory. And we are very fortunate in Canberra because we have Wombat XL. This is our brand new space simulation chamber. Essentially, it's a big vessel, 3 meters in diameter, 6 meters in length. We attach big pumps and we pump the air out to create vacuum or conditions similar to space. It is an absolute necessity to test the plasma rockets because access to space, one, is expensive. Space debris and pollution is already of great concern. And mostly, we want to get our astronauts back to Earth at the end of their mission. So in Wombat XL, we prepare for future manned travel to Mars. What I would like to do now is to invite some space cadets, rocket scientists, and future astronauts on stage to carry out some more experiments on plasma rockets. Okay, please come here, this way. I'll give you one tube. Give you one tube, just here. Hold it. Come a bit closer to me. Okay, so we're going to try and see if we can create a glow. Look at that. So what's happening here? It's called a skin effect. The current is going through the plasma. It's actually being carried at the surface of your skin and to ground. But you're right? And if I put my hand here, I get half of the current. This is a radio frequency signal, a bit like a radio antenna, radio emitter. So it travels at the surface of the skin, called the skin effect. We use this in our plasma rockets. You can see that the plasma doesn't go past your hand, so the current is going this way, and I'm not getting anything. If I put this here, I'm getting most of the current, you're getting a little bit. Let's try with you, just like this. There we go. Do you feel anything? No. That's good. So if you look at that, we can get both going. Excellent. So that's the first step. But we said that we are adventurous, aren't we? Yes. Well, we need a special device. Whoops, this way. Oh, wrong one. Here we go. That's a device. Here we go. To feel the skin effect, we use a spoon, which is a conducting metal. So you're going to hold the spoon like this. Do you feel the tingling? Yes. The bit of heat? Yes? Yes. Okay, how about you just hold this here now. You hold it here, and you can also hold her hand like this. And we're going to try this. Who knows? We'll see what happens. Huh? It doesn't work. Oh, we got one going. Yes? Big round of applause for our space cadets. Thank you very much. We have dreamed of space travel. We have landed man on the moon. We have established the International Space Station. We have explored Mars using unmanned vehicles. Now we are working on human travel to Mars. And I know that somewhere in this audience, it might be you who will be on that first round trip to Mars and maybe even beyond. Now, when I sit on a beach at night and gaze at the stars, I look for the bright spot, which is the International Space Station. You can see it when you have a clear, dark sky. And it truly inspires me and my work to think that one day a plasma rocket will travel from that space station, and the first humans will set foot on Mars.